Welcome to this lecture series in linear algebra. Let us recall what we need to know in this lecture. We need to know about cosets of a subspace. So suppose U is a subspace of a vector space V, then we define for each vector little v this thing as follows, and all such things that you can form are called cosets of the subspace U. Alright, we saw that cosets arise out of an equivalence relation. So you can define a relation tilde on the vector space V by declaring V1 tilde V2 if and only if their difference lies in the subspace, and the equivalence classes are precisely the cosets, and therefore cosets partition the vector space. And from the previous comment, it trivially follows that V1 and V2 are in the same coset if and only if their difference is in the subspace. Alright, we also need to know about set theoretic quotienting, which is the following. Suppose we have any function from a set x to a set y, and we collect the fibers, the non-empty fibers of f. So recall the fiber above y is defined as follows. And this could be empty, but you collect all the non-empty fibers, and that collection is denoted by this notation. This notation is coming from from just this equivalence relation called the fiber relation. Let me also subscript it with little f. So the fiber relation is the relation defined as follows. So if x1 and x2 are in X, then we declare that x1 and x2 are related under the fiber relation if and only if they have the same image under the function f. So the set of equivalence classes under this relation are precisely the non-empty fibers. And this map, this vertical map, is the natural projection map, which takes little x to the equivalence class that x is contained in. In other words, it takes x to the fiber x is contained in, and we get this map f bar, which takes the equivalence class of x to f of x. And this diagram commutes. The map f bar is injective. And we also saw a more general version of set theoretic quotienting, but we don't need that. All right, so let's continue with that. Okay, so the point of this lecture is to export this set theoretic quotienting to the linear algebraic setting. We will get to it in due time. So fix a linear map where the base field is f. Let me just say the base field is f, which by this I just mean that V and W are vector spaces defined over the field f. This is the set of scalars. Okay, let K be the kernel of T, which recall is this collection. All right, and here is the question we will answer. First, the question is, can we express or can we say something about the fibers of T? Of course, we will describe it in terms of the kernel of T, which is why we recalled the definition. So let's see. So fix two vectors, v1 and v2. Then they have the same image, which is to say that they are in the same fiber if and only if their difference is 0, of course, which happens if and only if by linearity of T, which is to say that the difference lies in the kernel of T, which means v1 and v2 are in the same coset of the kernel. So two vectors are in the same fiber if and only if they are in the same coset of the kernel, and therefore the non-empty fibers of T are precisely the cosets of the kernel of T. So we have a simple description of the fibers or the non-empty fibers of T. And this is just something that we needed to record separately. And now we can get to the main point of this lecture. Before we proceed, we will write instead of V modulo kernel of T, which is the same as the set of all the cosets of the kernel, we will write capital V bar. Just a notation, convenient. All right, so let us invoke set theoretic quotienting and see what we get now. We have a linear map T, and it factors through the set of all the fibers or the set of all the non-empty fibers of T, where this map is the natural projection and this is the map T bar. Recall again, V bar is same as V mod kernel T, which is, as we just saw, the same as the set of all the non-empty fibers of T. So this is just immediate from set theoretic quotienting. The map pi is V going to V bar, meaning the vector V goes to the fiber in which it is contained. Right, so perhaps I should have said this. The set of all the non-empty fibers of T is precisely the set of all the cosets of the kernel, but in which coset does a vector V lie, or in other words, in which fiber of T does V lie? It lies in V bar, which is just V plus by definition. That clearly V lies here because 0 lies here. All right, so the map pi just takes V to V bar. Okay. And this raises a natural question, or rather two natural questions. Question 1. Is there a vector space structure on V bar, which again let me emphasize is V modulo kernel T, such that pi and T bar are linear maps? So this was a linear map, but these two were just set theoretic maps because this was not a vector space. The question we are asking is, can we somehow equip this with a vector space structure so that the two other maps also come to the level of linearity, meaning this was not just some set theoretic map, this was a very, very, you could say, privileged map. It's a linear map. So they also feel like they should be linear. They are feeling left out. So can we equip this with a vector space structure so that both of them become linear simultaneously? And then the other natural question is, how many such structures exist? So there are three possibilities. Either there is no such vector space structure, in which case this is a dead end. What we are doing is, it is just some exercise in emptiness. Or there is a unique vector space structure, which indicates to the fact that we are heading towards some crucial truth. Right? If there's a unique vector space structure which makes both of them linear, there has to be that vector space structure has to be studied properly. That deserves attention. Or the other possibility is that there are many such structures, in which case it would be hard to decide which to use, or if any of them are useful at all. All right, so let's answer question 1 first. In fact, while answering question 1, we will have already answered question 2. So suppose there's a vector space structure on V bar, which makes, or such that pi is linear. So as of now, we are forgetting about T bar also. let's just try to find out what all vector space structures here, if at all they exist, make this guy linear. Let's first answer that question. And of course, having a vector space structure means having a function of this sort and a function of this sort, such that some properties are satisfied. So there is an addition here which we denote as plus, there is an addition here which we also denote as plus, and there is a fantasy addition and dot here which we also denote as plus. So these symbols will be abused, but hopefully will cause no confusion. So assume that there is some plus and dot defined here which make it into a vector space and which make pi linear. Let's see what we can say. So in that case, then by linearity of pi, we must have this must hold for all v1 and v2. Let me not write that. Again, this plus is coming from the vector space structure here, while this plus is inherent in the vector space structure of v. So this must happen, and which just means that this must happen. We are just using the definition of pi. And the other thing that must happen is, again, for all scalars alpha and for all vectors v, which says that, okay, so what does this tell us? This tells us that if at all there is such a plus and dot defined here which makes pi linear, then there is only one choice for it. You have to define plus so that it adds cosets of v1 and v2 to output the coset of v1 plus v2, where this plus is coming from v. Similarly, if you want to define scaling, then the scale of a coset, or rather the scale of the coset of v by alpha, must be defined as the coset of the scale of v. And of course, this scaling is coming from the vector space structure on the vector space capital V. So we are forced in our choice of defining a vector space structure here. There is only one such choice, if at all there is one. Right now it is not even clear that this is, defining things this way actually makes this into a vector space. Even before that, there is a problem of well-definedness. So what we are doing is, so the candidate vector space structure on V bar is the following. Define this map as the one which takes v1 bar comma v2 bar to this thing, which we may also write like this. So this is a definition, and define scaling. Oops. Which may be written as follows. Right, so this is a definition, but then there is a problem here because we are defining this via representatives. We are saying add two cosets. How? First find representatives of the cosets, meaning find v1 and v2 such that v1 bar and v2 bar are the cosets that you chose, and then just add the representatives and take the coset. If someone else takes some other representatives, then will we get the same coset? That is something that we need to check, but that is very easy to check because let's say, maybe I'll use a different color. So say v1 bar equals x1 bar and v2 bar equals x2 bar. Want to show that these two things are same. Right? So just realize this point. It is important to realize what we are doing. We are trying to show well-definedness of this, and we are saying that suppose we choose two different representatives for the same coset, and similarly for the other one, will we get the same answer here? That is what it means to say that this guy is well-defined. Okay, so what do we need to check this? That is, we need to show that the difference is in the kernel of T. That's what we need to do. But since we have v1 bar equals x1 bar and v2 bar equals x2 bar, we already have that v1 minus x1 is in the kernel and v2 minus x2 is in the kernel. So just add this with that, you get this thing is in the kernel. That's it. So this is well defined. Similarly, you can prove that this is well defined, and therefore at the very least these operations are well defined. But one must check. So check that this thing under the addition and scaling defined is indeed a vector space. Okay, so we have answered 1.5 questions. We have answered this as at most 1, and here we have said that there is a vector space structure on V bar which makes this linear. We haven't talked about this guy, but we have said that there is one vector space structure on V bar and exactly one which makes this linear. Now the question is, does that vector space structure make this linear also? If it does, we are done. Then there is a unique vector space structure here which fulfills our demand, and that deserves a special attention. Or it doesn't make T bar linear, in which case we just have to say that no, this answer is 0, and this was an exercise in emptiness. It was an important curiosity, but unfortunately that curiosity would end in despair. So let's just see if this vector space structure here makes T bar linear, and that will be the end of this lecture. So the point is, yes, indeed, T bar is linear. So our claim is T bar as a map from V bar to W is linear. And it's a very easy exercise. So let fix two arbitrary vectors in V bar, then what is this? This is equal to, by definition of addition in V bar, this is equal to that thing. And now by definition of T bar, this is equal to that thing, right? So recall set theoretic, this is just set theoretic quotienting. So we have the map T. Since this diagram commutes, V bar must map to T of V. This is what we have been saying all along. So this is equal to, by linearity of T, this thing, but now again by definition of T bar, this is equal to that. So we have verified that this guy is equal to this guy, and similarly you can show that this also happens, and hence this establishes the linearity of T bar, and we are done. So we have exported set theoretic quotienting to linear spaces, to the context of linear algebra. This was this was a linear map, while these were just some maps, but we have found that there is a unique vector space structure here which makes both this and that linear, and hence there is some special vector space structure on V bar which deserves special attention, and this will occupy us for the rest of the course. This is a very important construction. We will generalize it a little bit next time, and also see the geometric meaning of this addition that is here. It may seem very strange as of now, but if you just draw a little bit, maybe a few pictures, you will see what is going on, and we will flesh it out in the next lecture. Alright, so with that I want to end this. As usual, like, comment, share, subscribe, and I will see you next time.